All right, let's start with the revising what we learned last week. We started to talk about this topic called the analysis of organic compound. This is where we started. So in terms of analysis of organic compound, there are two types of the analysis too, of course, qualitative and quantitative, but we are more focused on the qualitative today. And we also started with this, the chemical tests that we know of those two. So quickly revising what the chemical tests are about too. We have, first of all, bromine water, the liquid, or the aqueous test. This is for the unsaturated, the carbon test as well too. In other words, by looking at the decolorization of the bromine water, we are able to note the presence of the unsaturated carbon in case of the alkenes. The second type of reactions, the chemical in the test we learned was the sodium carbonate, the test, also known as the carboxylic, the acid test. Basically, we put a little bit of a sodium carbonate, whether that be a solid or it could be a solid or the aqueous too. We're looking for the carbon dioxide production because carboxylic acids are the acids, sodium carbonate is a carbonate, so we just use the reactions of the carbonate and the acid. And CO2 it can be converted with the lime water test as well too. Third was this sodium metal or sodium test, and this is the sake of the to find the presence of the alcohol test. So what happens when we put the sodium into the alcohol? There will be some hydrogen gas produced, and we can confirm the presence of the hydrogen gas using the pop test of that too. Among the many of those two, we also learn about different type of the alcohols test. That's the oxidation test. Oxidation using the, if you remember the oxidation agents too, I just quickly write it down. Either be, but this the acidified dichromate or acidified permanganate, given that over here. Now, from that, we're able to know it's either be primary or secondary alcohol is produced or not. Okay. Now, same for these, kind of similar to that, known as the Lucas test, using the Lucas agent, using that zinc chloride and the concentrated hydrochloric acid as an agents too. This is a test for the tertiary alcohol as well as secondary alcohols too. What you'll be able to see there is, as adding some zinc chloride hydrochloric acid to a tertiary alcohol, there will be a little bit of layers we forms too, or a bit of a murkiness, and that indicates that that must be a tertiary alcohol. If the reaction is rapid, if that takes really slow reactions, it will be secondary alcohol, but primary alcohol would not have any of those givens too. You may also use the pH test for some of the amines as well as the carboxylic acid test too, or the indicators, but this is generally known as chemical test. And we discussed about these, the pros and cons of using that. Pros of using chemical tests, they are readily available chemicals that we have in the lab. So relatively easy process. As in like, so in terms of method, you collected like 5 ml of sample and test tube, you put a little bit of that to, you would know, oh, that's in something, that's some alcohol, that's in carboxylic acid. But cons, it's really big cons. It doesn't really tell us like the very specific carboxylic or very specific type of the functional group as well too. In other words, it's limited how much we can use from here. For example, sodium carbonate test can only be used for the carboxylic acid. It cannot be used for the alcohols. Same reason why sodium metal test will not be used for the carboxylic acid. Yes, this will be a reaction between metals and acid too, but as we know, sodium is highly reactive metals. You never ever put the sodium metal into the carboxylic acid if we assume that's acid. Okay, otherwise it will be explosions and that. There all will be like some of the also like safety precautions we have to follow every single time. Bromine is highly toxic, so you should not inhale that. Same for like carboxylic acid, corrosive. Sodium metal highly explosive, and all other things given too. So to overcome this kind of chemical test, we started to talk about the second type of the analysis. Chemical test or chemical analysis is the one we started with last week. Second type of that is called the instrumental, the analysis. And there are up to 4 to 5 types, up to 4 I would say, but you need to remember in terms of rules how to use that. We started with specifically infrared, in short IR spectroscopy. So what is the IR? IR is basically a really long wavelength. Or you may just think about anything like the light. That I press this button, the remote controls to it produce some infrared light too. This is like a less powerful than those of the visible light that we're seeing that too. So what happened is, as I described here, when this receive the energy, they kind of vibrate. Depends on the length, depends on the type of they bonded as well too. What we're basically doing is we're capturing the signals, the vibration basically here. And what we're able to see there is very specific regions and the way you have to describe the infrared was, if you remember that, there will be some signals in the number of the wave number in this unit. They set per centimeters like this. This is units that we have to follow. Excuse me. Okay, and there are very specific range of that. So the way you have to describe the signals of the absorbance, known as absorbance, is you need to describe that at first the strength of the signals, 2, the width of the signals at the certain range. Strength could be like strong, medium, or the weak. Width could be like the very broad, or like some narrow or mediums too. I already said medium is the one. And the range is the one that tells about where exactly, specifically what functional group we have. So what you need to remember is a bit of summary of that, guys, too, in terms of the infrared. We need to know if I'll always start with this carbonyl, the functional group. Okay, the range of that would be from following to the given the data here. It'll be around at 1682 to 1750 in terms of wave number per centimeters like this. And in terms of the strength of that would be really strong signals that you see. The width, however, would be like in the narrow. So in other words, if you can see that, a really narrow peak at around the 1700, this is indicating that there must be a carbonyl presented. Second is, the things I ask you to memorize is 2 types of the OH. One is for the acid, or just carboxylic acid form. One is for the alcohol. Now, the range of the acid. Now, remember that to be an acid, we must have the carbonyls presented. So you may think about this is with the carbonyls. This is without the carbonyls all the times too. Because in the alcohol, if the alcohol contains the carbonyl groups, it won't be like in the alcohol anymore. It will be a carboxylic acid, highly likely. The range of the acid is also followed to that given too. It will be given that as 2,500 to 3,000. Strength would be really strong, as well as width would be very broad. It's all well described on your page over here too. So the typical shape is very important. You need to remember. This is what like a typical shape of the OH. That's an acid. A typical shape of that. So very broad, as in like takes a lot of the surface area, as you can see. If you have alcohol, however, it would be the range of the 3,230 to the 3,550s, and it'll be strong, but more like a broad will be given to. So the difference between the OH of the acid to that is it would be look like this. The OH with the alcohols only will be like more shifted like that. Time to time you may see like a little fragments coming here like this too, or maybe longer than that. It doesn't matter. This is representing carbon and hydrogen bond, and this is OH. That's an alcohol. Make sure you memorize the shape. This is actually only the easiest method you can do. If you can recognize the shape by memorizing of the typical shape of those two, as you can see, OH acid would be really broad shape. One just big mountains, that must be a carboxylic acid then. But if we have that without the carboxylic acid showing kind of little like broad shape, strong signals with a little bit of CH fragments given, this must be alcohol then. Okay, you also need to know the NH. This is the between A minus and Gibbons 2. Now, A minus, even the range was given as the 3,300 to the 3,500. Now, A minus, remember guys, this is without the carbonyl again. Without the carbonyl like this. The signals, now, it could be varied. Strengths could be varied for the NH there. It could be strong, it could be medium, it could be weak, it doesn't really matter. But and the width would be like varied as well too, but not too broad. But the key point to understand the A minus is this shape. I call that as W shape or tooth-like. The shape as well too. If you imagine about tooth look like this, a shape of that tooth, you feel like a tooth root kind of shape. So time to time you make it the root shape like this on the top, or make a long root shape look like this. Okay, everything that is indicating that there's an A minus present is that too. Now remember that that's without the carbonyls. Without the carbonyl having just NH, this is the A minus. But there could be an NH, which is amide. Now, this is not really given on your formula sheets Gibbons 2. If you have an amide, the range could be varied, but it would be at around, I would say, 3,000s. What I mean by 3,000 is this is a 3,000 region, so you'll be somewhere located over here too. It doesn't really mean like shifted towards the left-hand side. You could be here, like look like this. Okay, but more like a broad shape of the Gibbons here. Strength would be kind of varied, but highly likely strongs. Width would be also be varied too. So what we're interested here is same, the W-shaped tooth-like a shape. If you haven't seen that W shape along with carbonyl, this must be a amide that we have Gibbons to. So I described it like in the kind of flow chart of how to figure out like the functional group. So what is the infrared and how do we use it? This is a very good for the function to determining the functional group. Especially for the carboxylic acid, alcohol, amines. It's a very, very good tools to use it. So if you have a carboxylic acid, by looking at the IR, you can straight away say that, oh, this is a carboxylic acid. This is well represented on your example that I gave you now today. Have a look at the prints, please. It shows all the samples of the A to Z, and you must finish everything, by the way, too, like answer all those questions. There's something we're going to work on later on, too. Have a look at the example data analysis that you have given. So this is a good example of that what I'm talking about in terms of infrared. The front page, the first page there. In infrared, the first thing you have to look for is 1700 regions, whether we have the long or strong, the narrow signals there. If we have that, that must be the carbonyls. Can you see that? Secondly, you need to look for the 3,000 range. If you can see that really kind of broad, very broad, it indicates that there must be an OH presented. Therefore, this is what? We have a carbonyl. Can you see the carbonyl there? As well as the, I turn the slide. Could you see that over here? Yeah, this is what I mean by carbonyl, the 1700 regions. This is what I mean by 3000, very broad, very edging, like one just big mountain shown to. This must be therefore a functional group of the carboxylic acid. And we can also confirm with the chemical test from the carboxylic acid test using sodium carbonate. the bubbles of the carbon dioxide forms too. So in the sign of that is carbon dioxide, therefore this must be carboxylic acid given too. So up to now, learning up to this here, you're able to know the functional group of the given two, but it's limited again too. I say it's really good for the carboxylic acid, alcohol, amine, but if we have aldehyde, ketones, esters, which shares the carbonyls, but they have a various kind of attachments too, the IR doesn't really specify giving you some ideas about those functional groups. And that's what the examiners like these days. We won't give you a question like carboxylic acid a lot of times in that reasons too. Aldehyde, which has hydrogen, is not sure. So we only see the carbonyl here, but he'll be like basically empty, basically like some random fragments. What you just need to remember for year 12 syllabus is figure out these patterns only, just only those. Okay? And so it's leaving us some good information about these random organic compound, but also leaving some limitation here again. IR is, again, just like a chemical test, it's very limited for the very certain type of the functional group too. It's good for those, but it's not really like universal to be used. 2, does it tell us the molecular shape or the molecular formula of this? The issue with that is it doesn't really tell us that what is exactly made of here yet. So to overcome these limitations, this is where we're up to last week. We started learning about mass spectrometry. So, a few things that you need to know about the mass spectrometry. 1, you need to know the procedure of the mass spectrometry. This is one of the famous questions that we get a lot in the school exams too, especially for the trials. Well, used to be, I should say, but you never know. So the way you can memorize that, oh, not this one. It's good to use the visual cue of this. Okay, that procedure is well described on your page 101 with the diagram to use. I recommend you to memorize as VRDD, VRDD or VRDD, whatever you want to feel like to do. VRDD stands for 1, vaporization, 2, ionization, A stands for acceleration, first D stands for the deflection. Last D is a detection. And you need to realize that every single part of those mass spectrometry is very important. Start with the vaporization. We basically heated up the organic compound, as most of those contains a really low boiling point. And basically in the gaseous state, they are separated. Ionization, we're using that, remember, electron guide. What they do, it will like bombard it onto those vaporized molecules too, and it kind of make the fragment. We're cutting those. But one thing that you have to understand for this is, if we have something look like this, okay, rather than just having the carbons like they're here, it was targeting on the carbon to carbon bonding a lot of times too, but something carbon with partially positive charge due to the electronegativity of the oxygen they're given like this. This will be easily get targeted by the electron, which is a negatively charged particles too. So a lot of time this will be bombarded on this kind of targeted on these carbons too, break the bond between these two. Not on this one here, because these are the basically same carbon. They have a more almost like a neutral charges. So the chance of the breaking this bond between the one carbon 1 and 2 is greater than chance of the breaking this bond between 2 and 3. So this is related to them fragments. So what information can we get from the mass spectrometry? Primarily, you can get the molar mass of the organic compound from the M and Z, mass to charge ratio of, remember this guys, called the molecular, the ion peak. So what is the molecular ion peak in that graph of the M and Z? And this is actually the intensity. But the way you can understand it is it's basically telling you the abundance, how much we have available to. The very last one, always the very last one, or the heavy one, is called the molecular ion peak. This is telling that, hey, the whole things basically get ionized by +1 charges too. Somehow they manage to just get everything get charged without breaking any fragments, and therefore we are able to determine the molar mass from that given too. One thing that students use, yes, they can read the number easily too, but in their answer, what they say is, hey, molar mass of this is this, straight away, without explaining that how the student actually got the answer. In your answer, you need to describe that as, hey, the molecular ion peak M and Z ratio is this. Therefore, the molecular and molar mass organic compound must be this. I know it can be bothered to write it down to sentences too, but you will get like 7-marker question about whole things that we're learning today too. And it is very important that how to write your answers at the end too. And because you may get this right answer, but you may not get the 5 out of 7 in that reasons too. This is the first information we can get, and so we are able to determine what? Combining with the infrared, combining with the molecular mass, we're able to actually can tell, okay, this is going to be something. Secondly, third, okay, is that from the fragments, we are the base peak from the either be a base peak or the fragments, we're able to know the possible structural, the formula with that given to with the functional group. So what do I mean by the base peak? First of all, base peak is the one that the tallest. This is the base peak. The tallest peak in there given is a base peak, and it's got to be always be 100% in terms of intensity is given to. From that, it's kind of telling us that this is the most abundant, like the fragments out of the many things. As I said, hey, if that's broken down, probably the most abundant would be either be these 2 carbons or this carbonyls attached to. So it's kind of telling us that it possibly having that contains that by looking at the charge to mass ratio here again too. And time to times, this is also used to determine that whether we have the ketone or the aldehyde as well too. Show the example. This is something that we didn't finish the last week. Have a look at the page. Page 117, please. Question 6. All right, we have 2 mass spectrometry for the isomers, isomer A, isomer B. Let's start off from that here. These are 2 isomers of the pentanone as shown below as 2. So pentanone, let's draw the pentanone guys first of all for A. Pentanone means 5 for pent. Pentanone is A stands for all the single bonds. O and E stands for the ketone group. So pentanone must be either be this one over here. But pentanone could be like many of those 2. This is the one example of the pentan 1-on. So you may think about the hydrogens kind of filling up. We may need that for the structure formula. Second type of that is we can have another pentanone. In case of this, we have a carbon is located in the middles, known as pentan 2-on, my bad. It was pentan 2-on. It should be a pentan 3-on. It would be the one given to, and the rest would be just the hydrogen. Yuri, what are these 2? What type of the structural isomers are they? Functional group, position, chain, out of 3. Same functional group, okay, same length of the carbons, but only the position of the functional groups given to. Can we actually get like something else too? What about we have a carbonyls if that's located here? Over here like this. And telling us this is no longer be a ketone. Hannah, what's the name of this? pentanal. It stands for the AL. We have carbonyls at the end, means that this is the aldehyde, no longer be a ketone groups too. Any chance you know the difference between, what type of the isomers are they? No. Jennifer, what type of isomers are they? No, there are functional group isomers. We have a completely different functional groups given, ketone and aldehydes too. Is there any chance we can get the chain isomer from this? Yes, you can. Okay, chain isomer would be like this: 1, 2, 3, 4, and we have a carbons and methyls then, with the aldehyde given. Okay, name of that would be like 1, 2, 3, 4. So 3-methyl butanol is the name of this. Okay, and these two are now we can say are chain isomers. We can also have a chain isomer from here and there as well too, specifically from this one. Pentan 2-on can have 1, 2, 3, 4, have methyls attached here like this too. And this would be like, the name of that, 1, 2, 3, so 3-methyl, 1, 2, butan 2-on is the name of this then given too. All these two are the chain isomers, okay? These two are the functional group isomers. These two are position isomers. These are the functional group isomers again too. Anything else? Any other isomers, David? Is there any possible isomers that we can get from here? Not really, okay. Now, let's think about like here. We have a structure of 2 isomers, the pentanol 1. So there are many, but the question is especially asking you this to here. So don't worry about for the others for now. Okay, we can have 2 types of the ketones, pentan 2-on, pentan 3-on. Depends on where the carbonyl is located. Easy, okay. Now, if we use but mass spectrometry, we're able to determine that which is that the pentan 2-on, which is pentan 3-on as 1, 2. First of all, no have to use about molecular ion pick because there are isomers, which means same molecular formulas, same molar mass with the different structures. So you're able to see that both of those would have a same molecular ion pick location here, which is around maybe like 86. And that would be like what? Same for the molecular formula of this here, so don't worry about this for now. C6, C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and O is the one that too. So in terms of molar mass of that, don't worry, you don't have to think about this one. It's kind of obvious. 5 times 60 and 66 and 76, 86, sorry, would be the molar mass of this, approximately. Okay, then you got to consider about here. During the process of the viability, especially the ionization, remember that electrons get shooted on the fragments to break them into here. Out of these two, okay, carbonyl, specifically this carbons, it will be easy target. Easy target for the electron because it is connected to the oxygen, which means it's partially positives too. Make sense up to here? Then when electron comes to this pentan 2-on, or either be like a pentan 1, it will either break this bond or this bond primarily, or even this bond and this bond primarily too. So I want you to think about the type of the possible fragments that we can get from the pentan 2-on, the possible fragments. From here, we can get the fragment of, if this is broken, okay, we can have CH3, okay, and the rest, if that is broken here, I'm talking about this breakage here, we can have a CO, COO, and CCC. Okay, I just write it down as this. So we have the 4 carbons, C4, H, 1, 2, 3, 4, 5, 6, 7, and 1 oxygen can be possible too. That's possibly a 1 fragment, second fragment. Make sense? Okay. What about this bond's broken? Then we can have this fragment comes out, which is C3, H7 would come out, and rest of those would comes out would be forms of the COCH3 like this. So in total, how many fragments are possible? How many like signals are we able to detect if this is pentan 2 on? We'll be able to see at least 1, 2, 3, 4, and finally the 5, the molecular ion peak in total number of that. Make sense, okay? Because everything in here got broken down. Like you can think about, we shattered all everything down to, put it into the this basic acceleration process, let them just spin around that too. We're able to detect the 5 of those given. Does it make sense at all? Well, what about this one? Pentan 3 on. Same process here, but the pentan 3 on goes into the ionization process. The carbon with the carbon, you will easily get targeted. Therefore, the bonding between the carbon to the carbon is targeted here too. So I want you to think about what the possible fragments that we can get. First of all, if this is broken down, we can possibly have C2H5, which is this section here. Okay, we can also have this section there, which is the C3H1, 2, 3, 4, 5, and O will be given as well too. True? Okay, what if this is broken then? What you have to realize is this is symmetrical. Therefore, it doesn't matter which bonds we've broken here, you always get the 2 fragments with molecular ion peak 1, 2, and 3. This is the minimum number of the fragments that we get. So by looking at that, compared to here, can you see now which would have the more number of the fragments, which is less number of fragments too? There's a chance that this isomer B of this mass spectrometry must be the pentan 3 on. And this would be pentan 2 on givens too. And we can confirm that with the base peak number. Now, have a look at the base peak guys here. And now, what's the base peak, the mass to charge ratio for this one, the first one? What's that number? 43-ish too. Now, do we have the 43 in here? No. Is that means if we can find a fragment with the 43 mass number, okay, that must be isomer A. Yep. Because it doesn't have the 43 mass number given to. So let's find out. Which will be 43? You can do the simple math in your head in here. Carbon is 12, hydrogen is 3. So mass number for each of those molar mass, this is 15. This is approximately like a 48 plus a 7, give it that 48, right? Okay, 55, and we have given the 16 given to 71 given. Okay, this C3H7 is 36 plus a 7, so 43. We have COCH3, 12, sorry, the 2 carbon 24, and we have 16, the 40, and 43. We have 2 43s given. Did I calculate something miss? 24, 16, 40, yeah, 43. 36, yeah, 43. What about this one? The molar mass of that is 24 and the 5, so 29 all together too. What about this one here? That must be 36 plus the 16, so 52 and 57. Now, from the calculation of the molar mass of each fragment, we figured it out. We only see that 243 in this pentan 2 on. Therefore, this must be the isomer A. This must be the isomer the B. How do we justify it? This is something that you need to study for that today too. Because this is the kind of trendy questions that we're getting nowadays in the HSC. In terms of that, yeah, guys, it's too easy to talk about read the numbers. You need to process the information correctly here. Based on the structural formula, based on the structures too, this carbon ions get easily targeted during the ionization process by shooting the electrons. Therefore, the possible fragments we can get from these pentantoners are these 1, 2, 3, 4, and the molecular ion peak. Each of these fragments occupies the molar mass of these much values too. Now, specifically that 43 is the only possible in pentan 2 on. It's impossible to get a 43 in pentan 3 on, guys. So based on that, and comparing to the base peak, all the individual fragments of the molar mass is given to, you're able to know that we only have 43 in isomer A, which represent this, therefore must be corresponding to isomer A, that is pentan-2 on. And you can also check your and confirm your answer. Do we have the fragment 57 in the next one too? We do have 57. Okay, so this must be what? That fragment of the C3H5O. That 29, this is 29 given over here around the two. Can you see actually they are corresponding to each other's givens too? Okay, this is possible for this here HEC. And this is something you didn't learn in school even. Okay, it's another higher level than what you learned. But as we try to give the questions a little complicated and trickier too for the all the examiners, remember that. Another type of question you can get is this. Could you think about a spoiler? You will get this one of the questions in your trial paper preparation later on too. Okay, assume that we have ester. Let's say, okay, let's make it an easy one. Ethyl ethanoate ester. This will look like this. Okay, now out of those here, actually, which carbon, let's say given number, carbon 1, 2, 3, 4, which carbon easily get targeted by the electrons? Carbon 2, because it has a carbonyl as well as it has oxygens too. This would have probably the most polar, most positively charged compared to other carbons givens too. Question is this, can you draw a mass spectrum like in a graph based on these structures givens too? We had that one question in a CSSA paper in 2020. It wasn't a question about given the graph, you asked to determine the shape. No, you're given this kind of things this, and you're asked to draw a mass spectrometry and justify your reasons for that. 7 marks, bam, that's it. Yeah. Now, what you need to think about here is this. We're going reverse of what information we can get from the mass spectrometry. What information can we get? First, we are able to get the molecular, the ion peak, which means the whole things get like what? The polarized too. So in the graph, make sure you put the correct like M and Z and the intensity in terms of 100% on the top. Percentage given here like this too. You got to find the molar mass of that first, which is the molar mass is corresponding to the M and Z mass to charge ratio of the this molecular ion peak. So counting that, how many carbons we have? 1, 2, 3, 4, 48, and 2 oxygens, which is a 32. 48, 32, we get 80. 1, 2, 3, 4, 5, 6, 7, 8. So 88 is the molar mass of that. You can do a quick calculation. So at the 88 over here, or you measure in the grids of that too, say 5, 10, 20, 30, 40, 50, 60, 70, and 80s. Okay, and 90, and go on to 88, show it specific over here too. You measure a little peak of that. It will look like this. That's the first thing you need to show. Now, which fragments get like a form from here too? So you can understand like the fragments can be formed by targeting this carbon here. Means that we can break the bond, number 1, or become A. We can break this type, B, or we can break this, even C, that too. This can further be broken down as well too. So this can be further broken down. D can be chopped. But highly likely, you can think of a percentage of that too. This carbon get targeted, so you may get either B from A and B most abundantly, rather than the C and D. Make sense? So the possible fragment from the A, then we can think about, we can have CH3 as number 1 we can get. We can have then rest of the A, this section, you can imagine, like if the A is cut, if the A is the cut, the rest would be this, the fragments given to, which would be 2 COO, and then we have CH2 and CH3. That's for A, from A cut. What about from the B cut? the cut B would produce that this section here. So from B, we get CH3 and CO, number 1, 2. I would say number 3. CH3 and CO. 4, that would get O's, all of the CH2 and CH3 like this. That's from the B cut. It's also because we get the C cut as well too, from the C. Then we get CH3, COO, the number 4, 5, the C, this cut, and the rest would be 6, CH2 and CH3 like this too. Then lastly from D, sorry, I'm running out of space, from D, the D cut, we get the CH3, 7 and 8, we can possibly have that too. CH3, COO, CH2 like this too. But remember that this is less likely to happen. So how many possible fragments we can get? We can get at least 8, but as you can see, 1 and 7s are duplicated each other too. You're kind of damping down into some smaller values too. Second thing then you need to do sure is this, the base peak, which could be the possibility like most abundant from the other givens too. You got to think about possibility over here. This A or B cut is most abundant too. So you may show that any of the fragments given over here would be most abundant. So you may see like if I assume this is most abundant here because COO is kind of targeting that or even that if values to givens too. I would actually say this one carbons, this carbons there. I would say this could be the base peak, the good candidate to base peak, because this carbon, again, is basically super polar, possibly charged. So this can easily get targeted. So in terms of molar mass, the charge to mass ratio would be, we have 3 carbons, 36 and 36, 72. We have 5, 72 and 77. So around that 77 region here, you'd get the highest peak look like this. Sorry, use a ruler, make sure you do that. Possible. Okay, and then the length, the height would be followed by the percentage of that too. You can have approximate percentage. Now, this doesn't need to be like correct. You're not a machine, by the way. But you can assume that based on your kind of logical justifications. Justification should be that this carbon is highly likely targeted from the ionization process because it is connected with the 2 oxygen, which highly likely are possibly partially positive. Therefore, the most abundant, fragment would be either from this cut A or cut B's. Make sense? Okay, and then you show the rest of those will be like some givens too. That's the 2 marks given. So I just show randomly here, guys. This is not correct. Like you may see like some things like this, like here. It could be anything. Then the last things you need to show is this isotope effect. 3 things we can get from here. Isotopes, especially for the carbon-13, carbon isotopes, or the hydrogen-2. As you know that carbon can have the possibility up to carbon-14 isotopes too. So even though like a percentage is really small, I would say 0.1%, if a lot of those available, you will be able to see that as in forms of that. This fragment will be like having some kind of hair structure look like this. Can you see that why? Because we may possibly get some of the isotopes of that too, and you will be able to see those will be shown as that. So you may need to show a little bit of this, not too many. 7 marks. Every single point of mass spectrometry must be shown. 2, you need to justify the reason behind it. This question wasn't possible if you didn't really study like a mass spectrometry thoroughly. That was one of the famous questions at the year, and then people were like, why are we getting this question? Why are we getting questions about something we practice to? Guys, the job of the examiners and the exam makers, we try to give you something that's assessing you, not giving you a question that a question you practice a lot of times too. So there's no point of the complaining about, I've never seen that question. Of course you never seen that. And same thing can be happening in HSC. I don't think like you would get these questions at HSC anymore too. It was really hard. The mean mark was out of 7 or around like 3. So majority of people failed. And not many people actually get a wonderful mark for these questions. But still be possible in the section of the mass spectrometry. Take a photo of that, yes? By the way, I'm recording the video for this, for the reasons. Yeah. The things that you need to know about isotope effect, as I discussed last week, chlorine and bromine. Guys, please remember that bromine has the bromine 79, bromine 81. We have a 50-50. Chlorine would have the 37 something, so you need to show the different peak numbers of that too. This is for the mass spectrometry for now. Okay, any questions? So, the first part is done. Let's move to the second part of the instruments. The analysis then. Page 122. Yes, notorious NMR now is given. Let's first then discuss about the limitation of this using mass spectrometry. It looks like, yeah, it does everything. It does kind of everything. It just tells about what. Okay, think about what information we can get from each of the instruments first. We're able to get the molar mass. Fantastic. We can get like how heavy they are. Two, we can possibly get the fragment we can possibly get the structures or the type of isomers by looking at the base peak or the fragment mass numbers too, which is good. Even though it's really complicated, I know it's complicated, but we possibly can do it. Isotope. We are also able to determine that whether we have isotopes as well too. Isotope as in like chlorine, especially for the isotopes, the halogens, those chlorine and bromine specifically too. Remember that this is the high chance we get the HS this year, bromine and chlorines. We had one in like 2022. Now what? 25. It's time to come back sometimes too. Now, good to use it. Compared to the IR, only tells you a functional group. This doesn't really tell the functional group, but if we can combine the functional groups, those of them the IR, as well as that, we can actually get what that compound is quite accurately. But do you remember from this pentan 2 and pentan 3 on that too? I only drew the 2 position isomers here, but we can actually have a lot of the isotopes given too. Isomers given too. Now, isomers in like they have exact same molecular mass, same compound, same basic carbon, oxygen, hydrogen numbers. But by looking at that, it's kind of limited whether they have methyls attached. Okay, well, whether they are aldehyde, or whether like they are actual structure look like too. This is the reason why you need to study the instrument called the nuclear magnetic resonance spectroscopies too, in short NMR. Now, what I actually described there about NMR is, this is like the MRIs of the spectrums, MRIs of organic compounds too. So what is the difference between MRIs and X-rays? Has anyone took the MRI before ever? It's not a pleasant experience, probably like you're probably going into a chamber with the really noisy sound there too. Now, difference between the X-ray and MRI, in short, X-ray use the light. Okay, basically same as that, you take a photo of yourself. Cheese, that's it. X-ray passes through, you get some structure in your shown too. All the structures that we talked about in here, especially of the IR, is using like an X-rays too. NMR, on the other hand, we're using some magnetic fields. It's kind of fancy terms too. We are using some magnetic like rotating around here, so that we're able to know whether we have a very specific things going on too. So if you think about the difference between the images of the X-ray, black and white, MRI is more color dieted too, 3D images. Basically, the difference of those is showing the very the clear picture of that compounds using organic compounds too. So you may think about this is like a small MRI machines for those organic compounds. The way we can do that is kind of similar too. So basically what we do is collect the sample, put it into the NS, which is showing the powerful electromagnets too. And depends on that, how they interact, we're able to capture that, the signals as well too. Make sense in terms of understanding here, how NMR working? Okay, I put those page 123 informations just for your understanding of the for a step study too. Don't worry about it. I put this as the least important for this whole chapters now. Because if you get questions about that, it's more like a physics rather than chemistry, to be honest too. This is possible for the, it's gone. Via DD is possible though. So how do we use it? So to understand that, we have to talk about something known as the chemical environments given to. So this is a page 124 that's given. Now, MRI, like NMR, again, is using the some magnetic field kind of things too. So depends on that carbons there too. So we got to talk about two NMRs, the carbon NMR or carbon-13 NMR, hydrogen NMR given too. Let's start off with the carbon NMR, but whether we're using carbon or hydrogens, we're using a very specific term called some chemical environments. So what does it mean by the chemical environments too? The way you can think of a chemical environment is you're looking into the some identical. So the way you can think about it here is this. I can give it here. Carbon is basically, you can think about the house. Okay? Hydrogen would be like occupant. Or you may say the family member. They're living in the house like this too. So I showed you what I mean by here. In case of this, we have a methane's given. Methane's given. In terms of carbon's environment, we're saying that there is no neighborhood. So you can imagine about those big houses in like some going into like a rural area, just one house itself too. There are one carbon living by itself in the house, and there are 4 occupants of the hydrogens inside of that too. In a way, think about this in the next one, which is the ethane. You got to think about one in here. Now, what we can see here is each of the carbons here have 3 occupants. So let's describe this carbon's environment. The way we can have to say that is think about first of all, who's living inside and who's living next door to. So what's living in this carbon's house? There are 3 hydrogen living inside. Can you see that here? Okay, and there's in the 1 carbon. What's in the next door? In the next door, we can say the carbon with 3 hydrogens as well too, with the carbon with of the 3 hydrogens. So I described that as, hey, this environment of this carbon is like this. It's living with 3 hydrogens. It has the carbon next door with the 3 hydrogen living next door too. But if we compare that, this one over here, it has exact same environment as the previous one we had before too. In terms of that, it has 3 hydrogens living inside, and there's a carbon with 3 hydrogen living inside too. So in the case of that, we only say, hey, there's only 1 carbon environment exists. That because there are basically what? The symmetrical, or known as the mirror image. So in the case we have a symmetrical shape that look like this, kind of ethane structures, we're saying that there is those environments are duplicated, so therefore we only say there's only 1 environment available for now. What about we have another like structures that would be like this? Propane. Also give it on your formula, your workbook too, but have a look. These propanes given too. So to differentiate that, I'll probably use the different colors of the carbons to help you. Blue carbons and the purple carbons given. Can you see here? Okay. Now let's describe first of all the blue carbons environments. Blue carbons living with 3 hydrogens. Okay. Next to the blue carbon's house, there are another black carbon with 2 hydrogens living next door. Okay. Does that make sense? What about the purple carbon? Purple carbon is living with 3 hydrogens inside. Okay. And next door there are black carbon with 2 hydrogens. Or it doesn't need to be the colors of the carbon with the 2 hydrogens too. What we can tell is, hey, comparing this blue carbon's environment to this purple carbon's environment, they are the same. And you can see that by in the middle line here, we can think about there's an asymptote like in the middle line here like this. They are symmetrical as well too. So We have one carbon environment for these two. What about the carbon environment in the middle then? Let's describe that again too. Black carbons living with 2 hydrogen inside, and next door there are two carbons with 3 hydrogens each. This is surely a different carbon environment for comparing these two given here. Does that make sense? So in this kind of propane, there are 2 carbon environments. One for the duplicated one at the edge or the end of those carbons, and one in the middle here like this. Make sense? Okay. Now what about we have very similar structure with the carbonyls, this time ketones given. How many carbon environments will exist in the case of this then? How many carbon environments will be given in case of this? Urine, how many carbon environments exist in for this? This is the butanol, by the way. There are 4. Why is there 4? So comparing each of the carbon environments, what can you tell about this carbon's environment? Can you describe this carbon's environment, please? 3 hydrogens connected. Carbonyls next door. Carbonyl next door too. You can think, oh, there's carbonyl living next door right now too. What about this carbon? This carbon is living with the oxygen. The occupants are living too. And there are CH3 next door. In the right hand side, there's a next door, and the CH3, there are CH2. And with the CH3, the whole thing's given too. So you make it in the middle of the lane of the straight houses too. This carbon is having 2 hydrogen living inside, and carbonyl and CH3. So even though these two, can you see like this carbon number 1 and 3? Even though they have carbonyl in the living next to those two, I cannot say they are the same environment due to the carbon 3 also have the CH3 living next door, and this one does not. Okay, same for in here. CH3, okay, there are 3 family members living the 4th carbons. So that looks like, compared to carbon number 1, which has the same occupant numbers too. But there are the different environment because this one, number 4, has CH2 next door and with the CO coming after. This has CO living after too. So they're all very separated carbon environments you can find in here. Does it make sense to understand the carbon environments then too? Okay, let's do a practice on these then. One, 2. Could you then determine the carbon environments for each compound, please? There are 10 carbon environments we have. Count the number of the carbon environment, please. I know it's hard, but try to enjoy the process of this, and you will need to. I know it could be the best, but it could be the worst. But have a look. Try to understand as what I said about carbon environments. You first look at how many things living inside, what type of those living inside too. You look at the next door. Okay, guys, it's a very simple question. You think about, if I ask you like your living environment, you have to describe about, I have my family members who living in the one house. You don't have to tell me what floors you're living in, like what street you're living into. I'm asking environment. And then you go, I'm telling about, there are people living next door. There's a family living next door. There's like some parents living next door too. This is how we describe the environment literally too. Same for the carbon environment first of all, and then we're going to discuss about the hydrogen environments after break. Carbon environments, you first look at what's inside here. So for example, the one in given 1, this is the ethanol. Can you see here, this carbon is living with 3. And the next door there are carbon with 2 and OH is given 2. 2, are they symmetrical? No. So can we say, this must be a carbon environment number 1 and 2 straight away like this? Easy. So there are total number of the 2 carbon environments given. Next one as well too, you got to look at the what's the carbon environment here, each of the individual here. Obviously, this is the very unique carbon environment, so you can give it number 1 straight away if you like to. Then look at next door here, living in 2, but there is carbon nil. So this must be a second carbon environment. Even though the third one here, living with 2 carbons inside, but you can see like completely different neighborhoods living next door to. Unique, 3. And 4, this is with the 3 hydrogen living inside, so completely different environments too. There are 4 carbon environment in that reasons. Next one is fairly easy. Just look, is it symmetrical? Yeah, very. So this must be, these two must be same carbon environment number 1, 2. There's only 1 carbon environment. So write it down, carbon there are 2, carbon there are 4, carbon environment there are 1 carbon environment then 2. Hannah, what about this one? We cannot do that too, but 3 carbon environment, very good. Telling me that every single carbon have very unique environments themselves given to. It's not hard if you try to understand now. Like guys, do it now. Like really a minute. Do it in the next 10 minutes to understand the whole point. Don't delay that till like a few weeks after. You will forget everything. Damien, what about this one? How many carbon environments did you find? 3. What are those?
The carbon connected symmetrical L1.
Yep. Number 1.
C with the double O.
Yep. This is number 2.
The C with the
3. Very good. So 3 carbon environments too. These two are not symmetrical, guys. It's a whole like you may think of the axis of the band. Okay. Jennifer, what about this one? How many carbon environments could you find here? 5. Indeed, each of the carbons are very unique in the carbon environments. You may question, oh, isn't these the same carbon environment at the end? No, looking at what's kind of connected here, they are very different. This carbon especially has a double bonds connected to, whereas this carbon is not. So you may say like all separated carbon environments given. Ashley, what about this? This is called benzene ring. How many carbon environments? 2. What are the 2? Should we describe it? Okay. This carbon, for example, having 1 hydrogen, double bonded, again, with the neighborhood, double bonded carbon with 1 hydrogen, single bonded carbon, 1 hydrogen. This carbon living with 1 hydrogen, double bonded carbon with 1 hydrogen, single bonded carbon with 1 hydrogen. This carbon living 1 hydrogen, double bonded carbon, single bonded carbon hydrogens too. What are they? They're all same carbon environment. So there's only be, even though we have 6 of them, it's only be 1 in their reasons too. Okay. Or you may think about symmetrical. This is symmetric. This is symmetric. This is a whole symmetry. This is why this is a ring or aromatic ring is kind of special functional group we use. Okay, Yuri, what about this one? How many carbon environments can we find in here? There will be. Yeah, I know these are symmetrical. What about carbon in the middle? Describe it. Can you describe the carbon environment of this one? One carbon with these Burkitt carbons attached, and how many occupants? 3 hydrogens. What about this one? 4 living in the house. Living in the house. So this got a really big house, must be. Completely different carbon environments you can figure out in here. Okay, guys, try to use that terms. By the way, the way I say about house, occupant, family members, you will never use that. It's not the term I'm teaching the chemistry, but just my job is try to make it as simple as possible too. Challenge, Damien. How many environments can we find over here? 8? 7? Okay, let's start with a definite one. Definite. This is a definite carbon environment. Same for this one over here. I mean, like, it cannot be the same. No symmetrical givens too. This carbon here, can we say it's a separate carbon environment? I mean, there's no symmetry and there's nothing really same. It looks the same as that too, so that'd be number 3. Definitely be givens too. Okay, and then problem is probably one inside over here. Let's have a look at what's it attached to. Let's start individually here. This carbon is out as a very unique carbon environment. Think about what I said about it, guys, here. Think about what's living inside, what's attached next door, like living next door too. This carbon living with the no hydrogen, but it's living with carbon, 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 oxygen too. Same for this one. This is very unique, I must say, because it is living with COOH. This is living with the Berkey OH gibbons too. Make sense? Okay. Now, what about these carbons? You may tend to say, oh, these two are maybe symmetrical here. Now, symmetrical means that mirror image, which means if we fold them, they should be exactly the same, symmetrically. Just like think about here. If I fold in any axis, they are symmetrical. So this is why we're saying these are the same images too. Is there any symmetry we can find in this ring, even though they say the same rings given? If I fold this direction, this direction, this direction, they will not symmetrical at all too. This is something important. They are not symmetrical at all. Means that every single carbons that we find in here are the separate carbon environment. Like this too. So in this reason why there are 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon environments. And I call this is the hardest question. It's really related to more to the some pharmacy questions. This is called the aspirin, by the way. That's what the aspirin look like. Oh, by the way, guys, this is a paracetamol, your Panadol structures given too. Because I got this from like some pharmacy university notes. What do we know? Anyone? Shall we start? Okay, with the definite one too. Demi, do you want to try again? 9. No, less than 9. 8? No, less than that.
7.
Less than that. 6 is the answer for this. Okay. No, actually, there's one more. 7. 7, actually, 7 is the one. This is definitely number 1 here. Same for the one we have. This is definitely number 2. I shouldn't circle the whole hydrogen, just the high carbons himself. 2. 1's gibbons 2. Now, what about this one? Can we say that it's a very unique carbons, gibbons 2. Now, problem started with this ring I get to. Whenever you get the ring, this has got to be harder questions too. So don't worry, you won't get too many rings questions. Maybe less, maybe none. This carbon, have a look. If I think about the symmetry of this, like this, you're able to see that these two are now in symmetry, in the mirror image. Just simply imagine that if I fold them, okay, in terms of axis of the whole thing, it should like a stretched line. So I showed it again. If that is look like this, nitrogen to carbon to the oxygens and CH3, it look like this too. If I fold the axis of in the middle here like this too, you may see that this is gonna be like folded, perfectly matching together too. Which means this carbon must be sharing the same carbon environment. In case of this, we have 1, 2, 3, that was 1. This would be 4, that would be 5, and individually 6 and 7. There are separate carbon environments that given to. Okay, so in terms of total number of carbon environments, there are 7 for this last questions that you have. Okay, I left that as the hardest question you can get. In general, up to here is year 12 syllabus in terms of how to figure it out, the carbon environments too. So guys, it won't be that complicated. Okay, I just gave that some in case like some school teachers giving some pharmacy questions. You never know, okay? But how to like it, you get questions like this. So I hope you understand the meaning of the carbon environment. I haven't touched the NMR yet too. To talk about the NMRs comes after them too. Any questions? Take 5 minutes break. We're coming back with some NMR after this then. All right, now we get it. We get it about, all right, these are carbon environment. It's all about symmetry. It's basically like telling about what they're living on, what their neighborhood is living on too. That's good. But how do we use them? How do we determine them? This is actually the main things we're going to learn about today too. In NMR, in the graph of the NMR is the carbon 13. We're especially using carbon 13s too. We have y and x axis that given here, and on your y axis there's basically nothing we have to worry about in here, but it shows that the chemical shift ppm shown in here like this too. And at the end of that, actually I drew the long bigger picture of this. It's better. We have things like this too. You can refer to the graph shown on the page 126 too, please. We have the chemical shift. That's a ppm that's given to. Now, at the end of that, we, unlike the other, like in some graphs of that too, we start at 0 at the end here like this too. And the numbers getting like increase on the left-hand side, going up to like the 40s, and you may think about the 20s, 10 and 30s. It could be like a more shifted too, doesn't really matter for that too. But most importantly, one, at the 0, we always have a peak called the TMS. They look like this. You don't have to know unless you're learning that in the schools too, but TMS, I would describe that as some sort of the standard or the control line of the whole magnetic field in the machines too. So we are putting some sample of TMS, which is made with the silicon dihydrate. So TMS is page 125, shows like this. This is basically TMS structures. Instead of the carbon, we're using silicon, which creates no kind of chemical shift because it's not the carbon. But you still have the carbons attached to it. It's kind of telling us that, hey, that's a 0, always a shift. Then, so in here, this is not really counted. Not really counted. We do not concern about TMS too much. This is basically control, as we don't really count about control in the experiments too. What is important? We are able to see that some of the signals at the very certain location of the chemical shift. So things like here, page 226. This is the chloroethane, having 1 chlorine attached to. Can you see like a purple and the blue colors there? Now, as we have clearly having 2 carbon environments, think about guys, carbon, purple living with 3 hydrogens. Next door there's a carbon with the chlorines living 2. This blue carbon living with the chlorine, so completely different carbon environments shown in here. This is indicated by the number of the peaks that we have. Okay. It's very simple. So the number of the carbon environment in CNMR is proportional to the number of the signals that we have given. Or signal or the peaks, I should say. Okay, that's the first information we can get. But guys, remember that here, number of the carbon environment doesn't really mean that number of the carbon. Have a look. Yes, for these, this would be like, hey, we have a 5 carbon environment and the 5 carbons given because each of the carbon environments are very unique. What about this one? We have total number of the 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. But there will only be 3 carbon environments. Due to that, the number of the symmetries too. So remember that this is also, it's basically related to the possible number of the symmetry. And that symmetry includes that some of the mirror images too. It could also be possible like the number of the methyls attached to. What I mean by this here, if we have 1, 2, 3, and this and that, okay, they look like these structures too. As we having a methyls attached here, this would have the 1, 2, and 3 carbon environments because the methyls always make the symmetry of the things given. Highly likely. So that's things you got to understand about the first information we have given. Second information we can get from the carbon NMR, well, C13 NMR is that we're looking into the position of the shift. Okay, so 2 is that from that position of the shift is representing that the more like electronegative, the kind of electronegativity or electronegative atoms or the and the element is presented. Please remember that more electronegative, negative element attached, we're making to the more greater the shift to greater the shift to the left hand side like this. The left hand side. And this is called the de-shielding effect. So what does it mean by the shielding of that too? Now, you can imagine about each of the carbons working on a shielding themselves from the magnetic field. So once magnetic field comes to, they have a shield, kind of like shielding the magnetic fields too. But when this is attached to the electronegative stuff, making this be partially positive too, the shield is kind of taken off due to the electronegativity. Which means that this carbon, for example, here, which is attached to the oxygen, is less likely to get protected by the shield due to the oxygen. Oxygen kind of taking the shield away from it. Same for the this two chloroethane given here. This carbon, purple, is well shielded because it has 3 hydrogen working as a shield. Can you imagine that too? But this carbon in blue is de-shielded, less shielded, because it has chlorines attached to. What it does is, it's kind of taking the shield of the carbons, making them to be more exposed to the magnetic field, leaving that the trail that this will therefore leaving to the more on the left-hand side of that too. TMS, have a look at the TMS structure here again too. Imagine that these are the perfect shield of every magnetic field. Think about silicon inside of here. You use the 4 hands of shield, up, down, up, right, and left. So it gets perfectly protected from the magnetic field. This is why TMS doesn't really have any shift, 0. But as we get the more shielded, get a more shifted left. So can you see them? Page 126. Purple is less shielded, less shifted compared to blue because it has more shielding effect. Simply it has more of the less negative, electronegative elements attached to these carbons too. So how do we use that? Why do we use that too? This is why we have this again too. In your formula sheets, you will get the data like this. Page 128, where I share the same data that we have too. It shows that carbon and NMR chemical shift data too. Depends on the location of the shift. We are able to determine the possible, not the functional group, the possible fragments of that too. For example, if we have the carbon to carbon, the shift will be varied too. Important thing is this, if we have carbon and oxygen like this, you have a shift to the 50 to the 90s, which means around the region 50, 90 over here, we'll be able to shift data is given us to. This represents one, that it might be the alcohol or it might be some, it might be the alcohol structures too. This one, carbonyl shown over here, can you see a 20 and 50 shift? This structure could be like ketone, aldehyde, or even for some carboxyl, any of the carboxylic gases too. So, in summary, the information we can get from this portion of the shift, we are able to determine that the possible structure of that fragments as well too. Does that make sense? So, think about what information we can get. One, we can get the number of the carbon environments. Sometimes we may be able to get the number of the carbons given too, if there is no symmetry given. 2, we are able to get the possible fragment shape by looking at the shift of that too. So make sure you use your formula sheet. We use the correct units of ppm all the times too. So for example, if you can see that shift at 30 ppm, you need to mention that in the answer, say, at 30 ppm, there's a chemical shift, the signal has become shifted, which indicates that possible fragment that look like this. Okay, and then combined with this on the mass spectrometry IR, you're able to know the actual structure of the givens as well too. These are the 2 information we can get from the CNMRs only. Kind of simple. compared to what I explained the carbon environments given over here. Does that make sense? Okay, so have a look at some example over here. It's page 129. Can you see that? We have given an ethanol. Now, ethanol has two carbon environments, one in blue, one in purple or pink, because it surely have the different carbon environments given. Now, what we can know, this carbon in pink would be more chemically shifted. Why is that? Because it's connected to, or they are bonded with the oxygens given. So this is a representation of these ethanols, therefore, too, telling us that. Have a think about without this key, you got to understand that there are two carbon environments, with one is more chemically shifted. Looking into your formula sheets, you're able to know the position of the purple and the pink is around the 60s. Looking into here, you'll get it's either be one of these given too. You can confirm that with some of the tests. This one is an ethane, which only has one carbon environment, as you can see. So therefore, can you see like it's really like less shifted? So it's having kind of like a kind of shielding effect, as well as so therefore it's not really chemically shifted, as you can see from that given. Easy to use a carbon NMR. What about next one, page 130, please. This is an alcohol. It's actually the ethanol itself too, so we have the same questions. Having the two carbon environments, so this must be the at least two carbon environments, and means that the minimum number of carbon must be 2. They're telling us that too. Maybe they're symmetrical here, but there must be like something that goes under here. So it could be very simplest structure would be ethanol, 2 carbons with 1 alcohol too. It's given the alcohol. Possibly some methyls too. It would have something like this. What if we have OH and we're having the 2 methyls? It's impossible to have that actually. Don't worry about it. Maybe that. This is possible too. Okay. Now, even though we have 3 carbons, these 2 at the end have these same carbon environments too. This is possible as well too. But it also tells us that limitation of carbon NMR. We can't really know like exact structures just by all the molecular forms given to. This is the reason why you need to know everything. IR, mass spectrometry, and NMRs too. All right, try the next one then, please. Page 131. Give you 2 minutes for this question then. We have isomers of the C3H6O. That's given. Okay? So, just by looking at the C3H6O, there are many possibilities. One, this could be an alcohol, having only 1 oxygen too. This could also be an aldehyde, which has only 1 oxygen as well too. This could also be a ketone too. We don't know. We don't know. This is why we have to look for the other things given too. Information given here is, however, we have given something, the fragments given here like this. First one, isomer A tells us that there are 3 carbon environments given. 3 carbon environments given. So any chance that we can get from these 2 information here, and the second thing is you need to look for the shift. This shift especially here. This shift to the 200. 200. Okay, Hannah, do you have the table? You don't have a table, do you? Okay. Here, could you pass one to the back? Same for you. Have a look at the data sheets and the shift table, please. Hannah, at the 200 ppm, what's the shift and therefore what's the kind of possible functional group? It's either be aldehyde or ketones too. Any chance that it can be the alcohol then? No. So from here, the shift at 200 over here, this 2 must be either be aldehyde or ketones too. We can get the information here. This is how you use your data and tables. Then This isomer A must be therefore, it's either be a ketone or the aldehyde with 3 carbon environment. Don't worry guys about 0, there's nothing that's shown here. So we count 1, 2, 3 carbon environments given us 2. So what can we tell about 1 is most shifted? That must be the carbonyl. That must be a carbonyl. Okay, now how do we get the 3 carbons with these 3 structures? It is possible with the aldehyde structure look like this. First of all, let's count the number of the carbon environment. There are 1, 2, and 3 in this propanol. Hydrogen numbers are matched as 6 hydrogen, 1 oxygen as well 2. 2, check that with the shift. This must be at around the 200 ppm, correct? Okay. What about this hydrogen there? Damn it. What about this carbons? What would be the location of the shift? Would be what? Which one? The middle and top one, which is around where? Around where?
40.
Around the 38 to 40 ppm. Now, is this matching to the data we have in the table? Is it matching? Guys, check your tables too. You'll be given that in your HS2. Is it matching to your table data? Yes. Can you see that part? Yes. What about the last part section there? This is basically telling you that around the, not even 10, around 10 values too. It's kind of corresponding data too. So this isomer A must be a propanol in that reasons too. This is how we use it. 2. What about this one? Again, from the last peak, around 200 ppm, this must be either be ketone or aldehyde. I showed you one method of the aldehyde in the isomer A. The possibilities then narrow down into not the aldehyde, but the ketone. We can only have one ketone with 3 carbons that look like this. That look like this. This is the only possibility that we can have. Can you see that? Okay. And this means what? We have 2 carbon environments. And this carbon in the middle must be that, the 200 ppm. That's represented in the last peak of the given 2. These 2 are relatively low shifted because it doesn't really get attached to the electronegativity stuff, which is the hydrogens only. Can you see that? And it's basically here. Guys, don't worry about the height of the peak. It doesn't really matter for this NMRs too. We don't really concerned. We are only looking for the horizontal shift locations. And the number of the peaks as well for the C NMRs given. Fairly easy. Yep. I'm just teaching you how to read the data, and that's all you need to know for now. Okay. All right, let's move on. The last of the instrumental analysis. Yeah, some would hate it, but some would like it. The notorious again, the HNMR is given here. All right. The idea for the HNMR, also known as proton NMR, is basically exact same to those carbon NMRs too. So NMR, remember here, NMR is all about MRI machines. We put it into some sample into the magnetic fields too. And then by looking at that shift, we're able to know. So just like the carbon NMRs, HNMR use the same term, means that we can also determine the number of hydrogen environments, not the carbon environments given too. So I write it down over here, the things we can get from first of all here. The first information from the HNMR, the H1, the proton NMR, sorry, it should be H1 NMR, H1. The first information is, just like the carbon NMRs, the number of the hydrogen environment. And you can guess, this is basically the same as the number of the signals or the peaks that we have. But what is hydrogen environment? I hope you get the carbon environments then, but hydrogen environment is a little bit different, slightly different to those carbon environments. So show some example of those using the two examples. One is the ethane. Another is ethanol. So OH will be Gibbons 2. Let's start with the ethane's Gibbons 2. The idea was for the hydrogen environment is somewhat very similar to the carbon environment. So first, you gotta look for how many is living together. So you gotta think about one hydrogen, this hydrogen perspective here. Okay, because we're looking in the perspective of the hydrogen, not the house carbons. This hydrogen in greens living with 1, 2, or in total number 3 inside. Yep. So can we say for this hydrogen's environment, there are 3 hydrogen living together. In terms of that, can we say these green hydrogens, so I must say the green hydrogen there, they're basically in the same situations to all the times too. They're in the same carbon environment living, they're in the same, so in other words, they are the same, they sharing the same environment. All the 3 hydrogens. Is it clear to everyone too? You can think about all your family members living in the same house, living in the same environment all the times too. Then, looking into the next, this is the blue hydrogen there here. Okay? In perspective of the green hydrogens, there are 3 hydrogen living next door in total number here. So total, the number of the hydrogens in next doors in the neighborhood, there are total of 3 hydrogen living next door as well too. But what about in hydrogen's perspective, the blue hydrogen perspective? This has living with 3 hydrogen members, yep, and there are 3 hydrogen living next door as well too in one house. So can we say these 2 are also what? The same hydrogen environment they're sharing as well too. So in case of that, just like a carbon environment, they have same hydrogen number environment, so there only be 1 hydrogen environment as well too. As we learned about the carbon NMR, applying the same rules for the H NMRs too, means that we only be able to see one peak Gibbons 2. Easy to understand the point? Okay? So again, number of the hydrogen environment will be shown here. But second thing is something very tricky and special about the hydrogen environments compared to carbon environments. Unlike the carbon environments, we care about how many are in the same environment, how many are actually living next door as well too. Okay, so for these, you have to understand the 2 points of this. I may create a tables too. Hydrogens in H, so you may say hydrogens within the same environment. Okay, and there are hydrogens in the neighborhood, living in the neighborhood. Create this table, please. The way we can determine that in the HNMR. Sorry, should go here. The features and HNMRs. The number of the hydrogen living in the same environment, we use in the term called the relative, the peak area. Is the way we can determine that how many hydrogen living in the same house too. Relative peak area is basically look like this. You can think about NMR structures there. We can have the structure look like this. Or having that area of this given here like that. So in case of that, this relative peak area kind of telling us that, oh, there are 5 hydrogens and 3 hydrogens on the top of that a lot of times too. Just guys, try to interpret here. This is called the relative peak area and telling us that this simply means, hey, there are 5 hydrogens in the same, exact same situations. They're living in the same situations too. Same question, same terms as that, oh, there are 5 family members living in your house. Secondly, hydrogen in the neighborhood is counted by something known as N+1 rule of that too, also known as the splitting of the signals. And it's called the neighborhood rules. So what we'll be able to see that is this. We can have sometimes a split of that too. This is called the triplet in the signals given to in HNMRs. Now, 3 split is 3 is given to. This means that according it's actual like the number of hydrogens in the next door or neighborhood must be 3 minus 1, giving that 2 is living next door to. This is called the N+1. Means N stands for the number of hydrogens in the neighborhood. So sometimes we can have this, like the pattern triplet. Sometimes we can have like 1, 2, 3, 4, 5. The 5 of the splits is shown to means that next door, maybe next doors, there are 4 hydrogen living next doors too. Even though it looks kind of complicated, this is very useful tools to determine the actual structure of that too. So it gives you some summary of that in here. So 1 is the number of the hydrogen environments, which is represented by the number of the signals and peaks. 2 is that we are able to know that the number of the hydrogens in the neighborhood. And this is using that N+1 rule and the splitting of the signals. 3, we are able to know that the number of the hydrogens in the same sharing the or hydrogen sharing the sharing the same environment by the rule called the relative, the peak area is the way we can do so. Yes, there is the 4th rules of the shift as well too. Position of each shift, which is also representing that this hydrogen next door is living with something electronegative as well too. So we don't really give a table for that in your data sheets, but from time to time you're given in the exam question in the HSCs too. If you have a separate table, it means that you got to use it too. It tells us that the electronegative, again, electronegative, the elements attached or living next door to, and also tells that the possible structure of the givens too. So unlike the CNMR, there are 4 information we can get from it. And remember that HNMR is used for these 2. Let's go through some example using that in here. The table for the shift, I give you some sample table on page 134. So you can see like it depends on how many shifts we have. You can be able to determine that what is attached as well too. In terms again, that will be given in your data sheet. So sorry, not in your formula sheets, given a separate paper on your exams too. N+1 rule. So page 136 shows the example of the given chloroethane again too. So chloroethane, as you can see from that, the structure, this chloroethane has 2 hydrogen environments, clearly. So you got to look for 1, how many hydrogen living together. So there are 3 hydrogen living together in the blues. Next door there are 2. So completely different hydrogen environment you can see from that. Make sense? Okay. So you got to think about it in here. These 3 hydrogens, how many neighborhood hydrogen living next door? In their perspective, there are 2 hydrogen next door. Yep. Can you see here? What about these 2? They have 3 hydrogen next door. It's very important that you clarify that they're in the living neighborhood, not inside of the same house, with 3 hydrogens. So 3H and 2H given. And 1 is with the chlorines attached as well too. So let's use the information here. As we have two separate hydrogen environments, can you see that we have a two separate this shift is given, signals given first of all. Secondly, you got to look for the shift. This red hydrogen living with the chlorines, attached to chlorines too, which is highly electronegative. Therefore, they are more shifted to the left-hand side. We call that de-shielding effect again too. Just like sharing the same information from the carbon environment. But as these two are living with the 3 hydrogen next door, this is important key. 3 hydrogen next door means that in their signals, they will see the splitting of the 4, which is the quartet, will be shown too. As 3 hydrogen means that according to M plus 1 giving there, 3 plus 1 giving 4, the 4 split will be shown there too. This is represented in here, 4 split. Can you see that? Okay, what about this one, the blue? Blue is living with how many? Living in the 3, but in the next door, there are 2 living next doors too. So N for that is the 2. So according to the M plus 1, the neighborhood rules, they need to have a 3 split, which is called a triplet. So it's shown the triplet, 1, 2, 3 splits shown too. Make sense? But think about how many hydrogen living next in the same house too. Red has 2 hydrogen in the same house. Blue has 3 hydrogen living in the same house too. This is represented in the red peak area, 2 and 3 on the top. So understanding that peak area is, hey, there are 2 hydrogens in the same environment. Split pattern of 4 means that there are 3 hydrogen living next door. So you got to interpret that as this region here. This region is therefore must be interpreted as there are 2 hydrogens in the same house, or the same environment, sharing the same environment, which is having the 3 hydrogen living next door, not the 4. M plus 1 stays for the N for that number of hydrogen, the quartet, or the number of split, telling us that you have to minus 1 of the split patterns given too. Looks not that bad, even though the shape of the graph is somewhat very complicated. So going back to your examples to, okay, sorry, before that page, let's finish the page 137 too. We have the famous example of the, again, ethane and ethanol is given. Started with the ethanol, ethane first of all, only has 1 hydrogen environment. Yep. Describe the hydrogen environments. We describe that as, hey, they have both have the 3 living together, and there are 3 next doors too. So in terms of neighborhoods, you can think about here. Each of the hydrogen carries that at least 1 here. So you will see 1, 2, 3, 4, 5. The patterns will be shown too. In terms of total number of hydrogen here. Make sense? What about this one? 3 hydrogen environments. Any objections? Disagree with that? Basically, blue, pink, and the red. Red with OH, that's also counted to the hydrogen environment. And then, so 3 splits will be shown too. The one most shifted would be the one in the pink, because that's living with the oxygen, not with the one in here. Or you can also follow to the data tables later on too. Now, let's think about the relative peak area. There will be 3 to 2 to 1 in the relative peak area, first of all. The amount of split, this is living with 2 neighborhoods. So must be split, the blue must split into the triplet. Pink, how many neighborhoods? There are 3. So it must be split of 4, quartet. It will be shown as 2. This doesn't have any neighborhood. We don't count the carbon in here. They're basically this far apart. You can think about this whole oxygen is kind of splitting the whole regions too. So it won't be like the same house or same region anymore. So this is kind of solely alone, so therefore there's no split of that too. In other words, if you have a singlet, just one, no split, highly likely shows that that hydrogen is isolated, indicating that there's a chance of that could be an OH given too.
Why is the red more shifted than the orange?
Because carbon, these hydrogens are living with the oxygen in the carbon's house. The oxygen, hydrogen is living, it's kind of attached to the oxygens too. When we're talking about the chemical shift, it's targeting more onto the carbon side too, not on the oxygen. Because oxygen is separately electronegative. So what this do is, yes, it's kind of surrounding the hydrogens, so let's kind of shield it. But don't worry about it. It's more about the carbons and living house too. Carbon is always be like describe the house they're living together to. Okay, all right. Could you try the page 138? Try this question then, please. So we have given C2H4Cl2. It's given the molecular formulas. Okay, so given that the HNMR spectrum is given, how do we first interpret that the NMRs?
There's 3 hydrogens.
3 or 2? Do we count the TMS?
3 hydrogens.
TMS is not even the carbon, it's a silicon.
There's only 2 hydrogens.
So there are 2 hydrogen environments. Does that mean, do we have any symmetry? Do we have any symmetry? Do we have any symmetry in the carbons? There will only be 2 carbons, right? Okay, and we have 2 hydrogen environments, unique hydrogen environments. There's no symmetry. They are very unique in terms of given. Okay, it's highly likely to be like, guys, this is highly like chloroethane, dichloroethanes too. Okay, actually, what else? What else? Yeah.
There's the 1 hydrogen, that one is like
Yep.
shifted the most to the left.
Mm-hmm.
It's likely the chlorine to attach to them.
Yep. So let's talk about the shift first of all. Then, the one has relative peak area 1 as most shifted. So more shifted. Means that this is the one that. What can we tell? This should be the one that attached to or living with. We're going to relate the chlorines there too. It's highly likely in the carbon cells that hydrogen must be living with the chlorines. Could be 2 chlorines or 1 chlorines, we don't know. But guys, have a thing here. If we have 2 signals, if we have this, I show you that. Possibility from that formula is we can have this. Yep, from the molecular formula given. Jennifer, how many hydrogen environments for this one? There's only 1. Can we get these graph, NMR graph from this molecule? No. So this means that 1 carbon has all the hydrogen, all the chlorines together too. This must be this. Chlorines in the same house and hydrogen in the one house given that too. This is only possibilities that we can get. So you need to write it down in case of this here. From the 2 hydrogen environments, the dichloro, 1,2-dichloro, the chloroethane wasn't impossible. Simply, that structure previously that I showed here has 1 hydrogen environment, which is not really matching to this kind of information given. 2, this indicates that 1 carbon contains both of the chlorine, 2 chlorines in the same house too. So this hydrogen must be, the pole hydrogen is rubbing into 2 chlorines too. This is why it must shift it to the left-hand side given as 2. Okay, times 2. And does it matching to that too? Yes. Relative peak area tells you about what? the hydrogen in the same environment. And then only one means that only one hydrogen having that situation of the living with the 2 chlorine, which is this one. Makes sense? Okay. Then, therefore, 3 hydrogens living with the same house, and there's no chlorine living next to each other. So shift is kind of like a less shifted. Yep. Can you see like 3 hydrogens? 3 is matching the numbers here. Now, in terms of the split, let's confirm that. This single hydrogen have how many hydrogen living next door? There are 1, 2, 3 living next door. So this number is actually corresponding number of the hydrogen living next door too. Therefore, the split must be the quartet, the 4th split. Is it matching to our data? It is. 1, 2, 3, 4. You can see that here. Yep. What about this 3 hydrogens? It only has 1 hydrogen living next door. Therefore, the split must be the doublet, which is a 2. It's a givens 2. And you should be able to write it down in words and sentences of how you interpret the data of the HNMR. As you can see, I just in the verbally spoken this here. It took me like a minute or 2. At least you need to write half a page of the page to fully understand, fully assure the full understanding of these HNMRs and to get the full mark of that too. Okay. What about this one? Oh, it's 2 chlorines is shown too, so don't worry about it for now. I showed the one HSC questions then, page 143. This is actually actual HSC questions, 2021, 1.5 is givens to. Now, let's start off from what we have given. So for these kind of questions too, I will provide you a summary of each of the instrumental things you can get. So copy this one down, please, in separate note. This is going to be a summary of every instrumentals too, and my guide.